In this video, we are going to talk about one type of scaling for the Navier-Stokes equations called inertial scaling. So inertial scaling. Okay. Now recall the incompressible Navier-Stokes equations are given by the continuity equation, div u equals 0, and the momentum equations, rho du by dt plus u dot grad u, put factor all of this out here, equals to minus grad p plus mu del squared u plus rho g. Now these are dimensional equations, and the first step in going dimensionless, we're not gonna talk much about the choice of scales, but typically in the problem you choose a length scale and a time scale, and then the rest can be expressed in terms of those scales. Or if you choose the length scale and the velocity scale, then you can determine time from those. We'll talk a little bit more about this, but for now, just bear with me. And the first thing we're going to do is we're going to choose the x scale, so that's x, y, and z. In other words, x star is x over some reference length scale L0. So for a pipe flow, for example, this could be the pipe diameter. For an environmental flow, this could be the height of the atmospheric boundary layer, etc. For time, we're going to choose a time scale called T0. But since we have a reference velocity, typically you choose either length and time or length and velocity and deduce time from those. But in this case, we're going to assume we know a velocity scale, and typically that's quite common. That could be an inlet velocity, for example, based on an inlet flow rate. So we can determine T0 from that velocity time scale, velocity scale. So we say that T0 is equal to L0 over V0, which is our velocity scale. In other words, this is the time it takes a fluid element moving at V0 to traverse a length of L0. That's what T0 is. So that means our T star is equal to T V0 over L0. Okay. Now U star will be equal to U over V0. And for the pressure, what we're going to do, we're going to choose P star is equal to P minus a far field pressure over some reference pressure to be pressure difference to be determined. Now, for the pressure, we chose a difference because typically it's not the value of the pressure that matters, it is the pressure difference that matters. See this grad P. So we choose a pressure difference because the absolute value of the pressure in and of itself is not going to be a driver for the flow. It is rather the pressure difference that will drive the flow. And with that, now that we have x and t, all operators as well will also need to be written in dimensionless form. So if you think about grad, the grad operator, which is d by dx, d by dy, and d by dz, we can write this as, now remember, x is L0 x star. So what you have is 1 over L0 d by dx star, and 1 over L0 d by dy star, and 1 over L0 d by dz star. And that is 1 over L0 grad star. In other words, grad star is equal to L0 grad, or grad is equal to grad star over L0. Okay? Now this is This is really important because it will allow us to convert all of the terms that appear here. So let's go ahead and do that. We start with the continuity equation. Div u is equal to 0. Now, we said that grad is equal to 1 over L0 grad star, and u was equal to V0 u star. So we have V0 u star, and that's equal to V0 over L0 div u star equal to 0. But since that's equal to 0, there's just these scales do not matter, so the continuity equation remains unchanged. Okay. Now let's look at the momentum equation. We have rho du by dt plus u dot grad u is equal to minus grad p plus mu del squared u, okay, plus rho g. Okay. Now we're going to do the same thing we did for the continuity equation. So we have rho. Now remember that u star was equal to u over v0. And so we have u equal to v0 u star. So we get v0 du star over t0 dt star, because t star was equal to t over t0, which was, but t0 was equal to L0 over V0, so that gives us t V0 over L0. In other words, we can substitute t0 over here. We'll do that in a second. Plus, what do we have here? U is V0 U star dot, what is nabla? The nabla operator, it is equal to, so remember, nabla was equal to 1 over L0 nabla star. So we get 1 over L0 nabla star, and U is equal to V0 U star, okay, equals to minus, we said that P is scaled, we defined P star as P minus P0 over delta P. Okay, now you can express P in terms of P star, and that's going to be, so you say P is delta P, P star plus P0. But since we have a gradient over here, then grad P0 is 0. So therefore, we get this equal to minus delta P grad P star. Agreed? Okay, great. Plus mu, what about del squared? We said that grad star was equal to, remember, grad star was equal to 1 over L0 grad, and so is div, we said grad is equal, and so is div grad is going to be 1 over L0 squared, grad star squared. So then we would have over here mu 1 over L0 squared del squared u, but then u is V0 u star, so I'm going to put V0 over here, okay, plus rho g. Okay, this is a very good first step that we started with. So now let's clean up some terms, collect some terms as needed, okay, and what we're going to do here is we're going to take out, we notice here that we have V0 over T0, and this term is, so V0 over T0, but remember T0 was equal to L0 over V0, right? So it gives us seconds. So we have V0 over L0 over V0, and that's V0 squared over L0. Now over here you have V0, that's V0 squared over L0, then they all factor out. And this makes sense because if you think of this guy, it's the material derivative, so it should be applied by the same factor. So this gives us rho v0 squared over L0 into du star by dt star plus u star dot grad u star is equal to minus delta p. Oh, we forgot here to put the star, so we have a star over here over L0, right? Because grad is 1 over L0 grad star, so this gives us minus delta p over L0 grad star p star plus mu v0 over L0 squared, okay, plus rho g. Now g, we didn't say anything about g, but we could, for example, just write it as some reference, g times some g star scale for the gravity, or we can leave it as is. So I'm just gonna write it as rho g, which is the magnitude of the gravitational attraction, and this is the gravitational vector. Okay, so that gives us rho g times g star. Okay, so now we have non-dimensionalized the problem, and if we have properly chosen the scales, then we are going to be able to make judgment calls on the relative importance of these terms. But we still have one unknown over here, and that is this delta p. And we have many choices about how we can choose this delta p. And one way to think of this is, okay, so let's get rid of the coefficient over here. We can get rid of this coefficient, or we can get rid of this coefficient that multiplies the viscous terms, okay? So which one do we choose? Well, one way is to say, okay, what is the relative importance of these terms? Do you think this is a high velocity flow where, or is this a slow flow where viscosity is going to be really important? Although that's not really strictly correct. It's the Reynolds number that determines the relative importance of viscosity. But if you think the flow is very viscous, it's basically just a creeping flow or a highly viscous fluid, then you want to divide by this term. Or if there's, a flow over an airplane, air flows, atmospheric flows, you probably want to use this term. We want to divide everything by this term. Another way to think about this is what do you think the relative importance of rho v0 squared over L0 with respect to this guy, or even that guy over there? We're not going to worry much about this guy right now. So in this video, we are going to do inertial scale, and that gives us rho v0 squared over L0 as the term by which we're going to divide. So in other words, we're going to multiply by L0 rho over rho v0 squared. So multiply equation by L0 over rho v0 squared. So when we do this, then this first term becomes du star by dt star plus u star dot grad u star is equal to L0 over rho v0 squared minus delta p over L0 grad star p star plus L0 over rho v0 squared times mu v0 over L0 squared plus rho g L0 over rho v0 squared g star. Okay, I keep forgetting the viscous term, so there's a viscous term over here, star squared u star. Okay, and now we can start canceling terms. So over here we get rid of L0 and we get delta p over rho v0 squared, and over here we get rid of this L0, we get rid of 1 v0, so it gives us mu over rho v0 L0, and this guy we get rid of this, and we get GL0 over V0 squared. And now some dimensionless numbers emerge. We still don't know what delta P is, but one way to think of this is actually the Euler number. But one way to think of this is that, say, you know what, in this problem, I think this term, this whole term is going to be really important. It's going to be almost similar to this term and that term. So I want to make this entire coefficient, I want to make this coefficient of order 1. So that's essentially a constant. It could be a significantly large value, but it's just going to be it's just going to scale with 1. It's a constant times 1. So what we say is delta P over rho V0 squared is equal to 1. So that delta P is equal to rho V0 squared. And when you do that, you knock out that term. So that helps us determine our pressure scale. We chose our pressure scale to be rho V0 squared. So this is technically rho V0 squared. So this is order 1. And the meaning of order 1 is just essentially means it's a constant times this guy. Okay, it doesn't scale. It's not a function of x or x squared. It's just a constant times rho V0 squared. So what this implies on the equations, so this term becomes 1, and then we would have du star by dt star plus u star dot grad star u star is equal minus grad star p star plus, now what about this term over here? This term is mu over rho V0 L0. Now if you remember the Reynolds number was equal rho Vd over mu, velocity times length scale times density over viscosity. So this guy is 1 over the Reynolds number. And this guy over here is nothing more than 1 over the Froude number squared, which we have looked at earlier, where the Froude number was V0 over square root of GL0. So this gives us the inertially scaled Navier-Stokes equations, 1 over the Reynolds number, del star squared u star, plus 1 over the Froude number squared times g star. And that is the dimensionless form of the inertially scaled Navier-Stokes equations. And all of these terms, if you take them in pairs, you can argue about their relative importance. But what you observe here is that these guys are not multiplied by any parameter that is going to reduce their or increase their relative importance. Rather, they're just almost all balancing each other. But then you come to the viscous term. As the Reynolds number increases, this term has less and less importance. Okay, so remember, this is the viscous term. And as the Reynolds number increases, doesn't necessarily mean that viscosity is going to 0. It could mean that the flow is becoming really, really fast. So therefore, the impact of the viscous forces becomes less and less important. The viscous forces will always be present, but their relative importance in the equation becomes insignificant, and therefore we can say, hey, we can neglect this term. Same thing for the Froude number. For very large Froude numbers, the gravitational term is insignificant. Remember, the Froude number was equal to V0 over square root of GL0. So when the Froude number becomes very large, as the Froude number becomes very large, this could be that the gravity becomes very, very small, or this velocity scale becomes much larger to be able to, such that it can escape gravitational effects, so this term can disappear. Okay, so if we take the large Reynolds number limit, then viscous forces become, or the viscous forces become negligible compared to inertial and pressure forces. Okay? And therefore, this term approaches zero. Doesn't mean that there are no more viscous forces. So this is technically not an inviscid flow, but we call it inviscid. But that's the wrong nomenclature. It's just that the viscous forces are so negligible that they have no effect on the governing equation. And this is how you get the Euler equations. Okay, so if you neglect this term, you can also neglect this term or keep it. And then you get the Euler equations, which have been dubbed inviscid flow equations. It just means that viscous forces are negligible. Okay, so it's or a region of the flow where viscous forces are negligible. And this approximation is typically valid away from boundaries, up in the atmosphere, an airplane flying the entire region away from the airplane could be assumed to behave in this manner. Okay, so certainly when the viscosity is very small, the Reynolds number also becomes very large, and then therefore this term starts disappearing. So this is very valid, you know, airflow, airplanes, away from boundary, etc. But ocean currents can sometimes be approximated this way, ocean currents, compressible flows, okay? And this gives us the Euler equations. Now, this breaks inside the boundary layer, because then within a boundary layer, and we'll talk about this a little bit later, when viscous forces become important, then the Reynolds number becomes small. And then one way to think of this, if you multiply this whole thing by the Reynolds number, then you see that this term starts dominating. But if you multiply by the Reynolds number, you're going to lose the pressure, and we don't really want to quite lose the pressure in this case. So we would have to use another scale for the pressure, and that will be discussed in the next video.